Graphing Rational Functions, Part 2. Previously, we talked about vertical asymptotes, domain, and holes. Now we're going to talk about determining what's called horizontal asymptotes. Horizontal asymptotes are found by looking at the exponents of the leading terms in the numerator and in the denominator. As a helpful hint to remember the rules, here's what I've come up with. Bobo lets you know that the degree is bigger on the bottom, and if so, it'll be of the form y equals 0. Bosco means that the degrees are both the same, which means the horizontal asymptote will be of the form y equals coefficients. The last one is Botno. That means when the degree is bigger on top, then you have no horizontal asymptotes. So these are helpful, but let's see why are they the way they are. Looking at Bobo, when your degree is bigger on the bottom. Well, let's look at some numbers. If I were to look at the fraction y equals 1 over 10, and say I made it y equals 1 over 100, and maybe 1 over 1,000, and then 1 over 10,000. If I continue that pattern, these fractions are continually getting closer and closer to what value? Well, they're getting microscopically close to a value of 0. Now, if I were to put this as a function, say x over x squared, do you agree that the degree in the denominator is bigger? Well, if I look at that function and I plug in values, if I plug in a 10 into that function, that becomes 10 over 10 squared, or 10 over 100. Notice that fraction reduces to 1 over 10. What if I plug in 100? So 100 over 100 squared. Well, that gives me 100 over 10,000. But that fraction reduces to 1 over 100. And I try another value, and it also reduces. But notice, although I keep trying larger and larger values, what's happening to the result? All of them are getting closer and closer and closer to what value? To 0. So that's why if the degree is bigger on the bottom, the ultimate result is getting closer and closer to 0. For Bosco, let's look at this one. This is when you have the same degree. If I were to look at y equals 1 over 2, and I were to change that to y equals 10 over 20, or maybe 100 over 200, or maybe 1,000 over 2,000. Notice they were always written, the numerator and denominator were written in the same terms, whether they're tens, hundreds, thousands. Each one of those reduces to what value? Well, they all reduce to 1 over 2. Now, if I look at this as a function, say x over 2x, and I plug in values, say I plug in a 1, well, that gives me 1/2. What if I plug in a 10? Well, 10 over 2 times 10. Well, remember, the 10s can reduce, so the result is still 1 over 2. What if I plug in a 100? Well, here it also reduces. So as I continue to plug in larger and larger and larger values, what does this always equal? In this case, it will always equal 1 over 2, which happen to be my coefficients of the original function. For Botno, it means when the degree is bigger on top in the numerator. So say I had 10 over 1, or 100 over 1, 1,000 over 1, even 10,000 over 1. As these numbers increase, what number are they getting closer and closer to? Well, it turns out they're not getting close to any particular value. These numbers are getting larger and larger and larger. They're getting closer to infinity, but nobody knows exactly where that is, so we simply say there is no value. It's not getting closer to a particular number. So if I look at it as a function, say x squared over x, and I plug in values such as 10, that makes it 100 over 10. Now again, it reduces. Say I plug in 100, and then I reduce. I plug in 1,000, and I reduce. But as you look at the results, are the results getting closer and closer to a particular value? No, which means there is no horizontal asymptote. Now, looking back at our previous examples, example 2, for a we had f of x equals x minus 2 all over x squared minus x minus 2. We're now going to go back and identify the horizontal asymptote. It's easy to identify the horizontal asymptote when the function is written in expanded notation. So looking at example A, we look at our leading terms. We have an x over x squared. And so we ask ourselves, is it bigger on top? Are they the same, or is it bigger in the bottom? So is this Babo, Bosco, or Botno? In this case, this is Babo, which means bigger on the bottom. So therefore, your asymptote is y equals 0. For b, we had the function f of x equals negative 2x squared minus x plus 15 all over x squared minus x minus 12. Again, we're looking to identify the horizontal asymptote, so we look only at the leading terms, the highest degrees, which means we focus in on negative 2x squared over x squared. Is this Babo, Bosco, or Botno? Since they have the same degree, this is Bosco, which means both the same, so we are going to look at the coefficients. In this case, our coefficients are negative 2 over 1, which does simplify to y equals negative 2. Now, we have talked about vertical and horizontal asymptotes, but I want you to know there is another type called oblique or slant asymptote. We will not cover it in depth here, but I want you to know they do exist. An asymptote is not part of the graph. The graph never crosses a vertical asymptote, but the graph may cross a horizontal or slant asymptote. Think of it this way. A vertical asymptote is like the law. A horizontal or slant asymptote is like your parents' rules. Sometimes as kids, we test our parents' boundaries. So we may cross it, other times we may not. Now, steps for graphing rational functions. The first thing we're going to look for is identifying any horizontal asymptotes. We identify this when it's written in expanded form. That's also when we're going to use Babo, Bosco, Botno. And it will be written as the form y equals whatever the number happens to be. The second thing is we will state the domain and any possible holes. This is identified by looking at the factored form. Remember, holes are found by common factors. Third, we identify any vertical asymptotes. This is found when the function's written in reduced form. If you do have any vertical asymptotes, it's written of the form x equals some number. Number 4, we then find x-intercepts, or our zeros. To do that, we take the original function and we set it equal to 0 and solve. In the process of solving, it always ends up being setting the numerator equal to 0 and then solving. Number 5, we find the y-intercept, and the y-intercept is always where x equals 0, and then we solve. And then the last step is we graph this information, and then we find additional points. Let's look at an example. Example 3, graph the function f of x equals, and in the numerator we have x squared plus 3x all over, and in the denominator we have 2x to the third minus 5x squared minus 3x. And in this problem, we are going to be identifying the 1, horizontal asymptote, 2, the domain and any possible holes, 3, vertical asymptotes, 4, x-intercepts, 5, y-intercepts, and 6, then we will graph. Let's start at the first step. To identify any horizontal asymptotes, we look at the original function, and we identify the leading terms. This is where we use Bobo, Bosco, or Botno. So look at your degrees, your powers. Is it bigger on the top? Are they the same, or is it bigger in the bottom? Since the degree is bigger in the bottom, this is Bobo, which means your horizontal asymptote will occur at y equals 0. Now we're ready to look for domain. To identify domain, the function has to be in factored form. So take a moment now to factor the numerator and the denominator completely. In the numerator, there is an x in common, leaving you with x plus 3. In the denominator, there is an x in common, so you factor that out, but it's still a quadratic, so it needs to factor again. And in the denominator, when you completely factor it, you will now have x times 2x plus 1 times x minus 3. Now that we've got everything completely factored, we focus on the denominator. In this case, we have 3 separate pieces that are all in the denominator. We have an x, a 2x plus 1, and an x minus 3. So we set each of those pieces equal to 0 and solve. You will find that x cannot equal 0, x cannot equal negative 1/2, and x cannot equal 3, which if you put that on the number line, you will find your domain is negative infinity to negative 1/2 union, negative 1/2 to 0 union, 0 to 3 union, 3 to infinity. Now also in the factored form, we can identify if we have any holes. Now holes are found by common factors. Do you see any common factors? Yes, we have an x appearing in the top and in the bottom, so we do indeed have a hole. Now to identify the hole, we take whatever the common factor is and set it equal to 0. In this case, our common factor is x. We set it equal to 0, which means x equals 0. Now we cannot find the y value yet until we have the reduced form. So let's continue on. Now to identify the vertical asymptote, we have to have the reduced form. So we've already had it factored. Now if we remove the common factors, we see that the reduced form of the function is x plus 3 all over 2x plus 1 times x minus 3. The vertical asymptote is identified by using the reduced form, and it's any of the values that cause the denominator to equal 0. In this case, our vertical asymptotes will be x equals negative 1/2 and x equals 3. Now that we have the reduced form, now we can find the remaining part of our hole. Remember, to find the y value, you must plug in the specific x value into the reduced form. Well, for us, our x value is 0. So we plug a 0 into the reduced form and then we simplify. Take a moment now to simplify and see what you find for the y value. Hopefully you find when x is 0, y is -1. So your whole occurs at 0, -1. Now we're ready to identify our x-intercepts. X-intercept is where y equals 0. So we go back to the original function and we set it equal to 0. From here, what we want to do is, because we started with a fraction, I want to eliminate the fraction by multiplying the left side of the equation and the right side of the equation by the common denominator. In this case, my common denominator is x, 2x plus 1, and x minus 3. And what you notice is on the left side, 0 times anything is still 0. And on the right side, if I multiply the common denominator and it has already the same denominator, it will reduce, which will just leave you with the numerator. So I now have the equation 0 equals x times x plus 3. This equation is much easier on the eyes. From here, since it's already in factored form, we take each piece and set it equal to 0. The first piece, x equals 0, is already solved, but the other piece, x plus 3 equals 0, well, that still needs to be solved, so we subtract 3 on both sides, and we find x equals -3. So it appears we have two solutions, but you have to check. Are both of these numbers in the domain? No, it turns out 0 is not in the domain, so we cannot include it, but -3 is okay. So we have to write this as an x-intercept, which is a point, which means it will be -3, 0. Now for the y-intercept. Y-intercept is simply where x equals 0. So we take the original function, we plug in a 0 for every time you see x, and then we simplify. Well, 0 squared is 0, 3 times 0 is 0, 0 cubed is 0, 0 squared is 0, 3 times 0, there's a whole bunch of zeros going on, and when you simplify, you're left with 0 over 0. Now, can you divide by 0? No. This is actually undefined, which means there is no y-intercepts. Now let's graph. So go ahead and take a moment to draw your xy axis. Okay, looking at all the clues we already have, the first thing is we are going to draw our horizontal asymptote, which is y equals 0. So we draw a dashed line along the x-axis. Next, item 2 is we have our hole, and our hole will appear at 0, -1. So remember, a hole is an open point, so it will be an open circle. Next, for number 3, is we have our vertical asymptotes. These are vertical lines. The first one appears where x equals -1/2. Again, we draw a dashed line. And we have another vertical asymptote at x equals 3. So we draw a second vertical line, dashed, and make sure you do label all your asymptotes. Next, number 4, we do have our x-intercept at -3, 0. This is a point, it is a closed point, so go ahead and draw that. And notice we have no y-intercepts. So next, we have all the markings of the graph, but now we need to start looking at particular values. So we are going to create a t-chart. First, because we have so many different things going on, we want to look at different regions. The first region we are going to look at is the region to the left of our x-intercept. And so to the left of it, I want to choose one value that lives in that shaded region. And I'm going to choose -4. And from here, what we're going to do is choose values in between each characteristic so we get an accurate representation. Let's look at the next region. The next region is between -3 to negative 1/2. Well, between those two values, you may see there's a -2 and a -1. So those are good x values to add to our t-chart. The next region is between the vertical asymptote and the whole. So a small sliver. But we do want to see what's happening, so we choose a value of -1/4. The next region we want to check is between the whole and the vertical asymptote of x equals 3. In that region, we see x is equal to 1 and 2. So we add those values to our t-chart. The next region is to the right of the vertical asymptote x equals 3, and in this region, let's select where x equals 4. Now that we have selected all our x values in our t-chart, it's now time to find the corresponding f of x value. You may either now choose to plug the values in individually, or you can use the table feature on the calculator. But use your time now to find the corresponding y values. Hopefully you found the same values as me, or they're pretty close of. -4, -0.02, -2, 0.067, -1, 0.5, -1/4, -1.7, 1, -0.67, 2, -1, 4, 0.77. Now that your t-chart is complete, take a moment now to plot these points on the graph. Hopefully your graph looks something similar to mine. Now remember, your graph will never cross a vertical asymptote, but it might cross a horizontal asymptote. And we do see an example of that because we do see an x-intercept along the left-hand side of the graph.